Okay, so today I want to go ahead and look at section 3.5. 3.5 is where we're going to prove the double angle and half angle identities. Now, the double angle identities, we're going to go ahead and begin with the sine of 2x. Now, sine of 2x is 2 sine of x times cosine of x. That is the double angle identity for sine. We're going to prove it here real quick. Now, the sine of 2x just means the sine of x plus x. That's really all it means, right? But if you notice, that's just the sine of a sum formula. Now, out of curiosity, off the top of your head, do you remember the sine of a sum formula?
Cosine plus, actually, I don't know.
Here, let's put it. If I have the sine of alpha plus beta, what's that going to be?
Cosine alpha plus cosine beta minus sine alpha plus sine beta.
No.
Isn't it sine alpha?
The wrong.
Good.
I was clearly wrong.
Sine alpha cosine beta plus cosine alpha sine beta. Notice that sine is odd, so it means that these two have to be opposite functions. The one that you told me was the cosine of the sum formula.
I'm just wrong because instead of multiplying, I added in between.
Well, yeah, that was wrong too. But you also used cosine and cosine and sine and sine. When they're the same, that's cosine.
So when it's cosine, it's going to be the same on each side?
Yeah.
Oh.
Cosine and cosine, sine and sine, with opposite in between.
Oh, okay.
Yeah. Good deal. So sine of x plus x would then be, well, if we plug all that in, helps if I use that. Well, if we plug all that in, that's going to give me the sine of the first one, x, times cosine of the second one, x, plus cosine of the first one, x, times sine of the second one, x. But notice that sine x, cosine x, plus cosine x, sine x, sine cosine is the same thing as cosine sine, right? They're the same thing. So if I add them together, this is going to give me 2 sine of x, cosine of x. QED, we're done. That is the double angle identity for sine. So we're okay with that? Not too bad. Good deal. Now let's look at the double angle identity for cosine. So for cosine of 2x, we're going to look at as cosine of x plus x. Out of curiosity, do you now remember the cosine of a sum formula? Cosine of alpha plus beta.
Cosine alpha cosine beta plus sine alpha sine beta.
Almost. Minus. Cosine alpha cosine beta minus sine alpha sine beta. Good deal. Now, coming down here, alpha is going to be x, cosine is going to be x. So if I plug all that in, that's going to give me cosine of the first one, x, times cosine of the second one, x, minus sine of the first one, x, times sine of the second one, x. Fantastic. Now, notice that cosine times cosine is just cosine squared. So it's going to be cosine squared of x minus sine times sine is sine squared. So that'd be sine squared of x. And so again, the cosine of 2x is equal to cosine squared minus sine squared. Good deal. So we just proved the double angle identity for cosine, but notice there's more than one there. This is just the one that we got immediately, the cosine squared minus sine squared. There are actually 3 different double angle identities for cosine here. To get these other 2, we're going to use this one and then use the fundamental identity of trigonometry. Coming up here, what is the fundamental identity of trigonometry? I would hope you know it because it's the fundamental one, right?
Yeah.
Cosine squared plus sine squared equals 1. You'll always see it written down though, usually as sine squared plus cosine squared. I don't really know why we do sine squared plus cosine squared instead of cosine squared plus sine squared, but we do. So there you go. That's the fundamental identity of trigonometry, right? So what I can do is I can take that idea down here and I can replace either cosine squared or sine squared with what it is. Up here, notice I could solve for sine squared by subtracting cosine squared, right? And so that would be 1 minus cosine squared. And I can solve for cosine squared by subtracting sine squared. So that'd be 1 minus sine squared. So coming down here, which one do we want to do first? 2 cosine squared? Okay. So we're going to replace this sine squared with the 1 minus cosine squared. So whenever we do that, that's going to give me cosine squared of x minus parentheses 1 minus sine squared of x. Notice if I distribute the negative and combine, sorry, it's 1 minus cosine squared. I'm going crazy. Don't yell at me too much here. Should though. When I distribute the negative there, it's going to give me -1 and a plus cosine squared. So we're going to have cosine squared of x minus 1 plus cosine squared of x. So notice that we have a cosine squared plus another cosine squared. That's going to give me 2 cosine squareds of x minus 1. That is also the cosine of 2x. That's another one. We would do the same thing again for the next one, where we would replace the cosine squared with 1 minus sine squared. So this is going to be 1 minus sine squared of x minus sine squared of x. And then combined like terms gives me 1 minus 2 sine squared of x. And again, that's another one. Fantastic. So there we go. We have just proven all 3 of the double angle identities for cosine. Double angle identities for cosine here. Any questions about the sine or cosine double angle identities? So these are the proofs of them. But we also have one more. We have the tangent double angle identity. And I have simply run out of room there, so I'm going to come over here. So over here, we're going to ask, first of all, what is the tangent double angle identity? Preferably without looking it up. See if you can do it.
Then
In alpha,
Oh, you could derive it. Yeah, you could do it that way, but I wouldn't.
no,
I would just memorize it.
would it be like tangent alpha?
Tangent alpha,
Beta,
tangent alpha plus tangent beta
over
all over
1
1
plus
minus, good,
minus, no,
tangent alpha,
tangent beta.
tangent beta. So tangent alpha plus tangent beta all over 1 minus tangent alpha tangent beta. That is the tangent of a sum formula. But what if alpha and beta are the same thing? In other words, what is the tangent of, say, 2x? Well, tangent of 2x is tangent of x plus x, just like we did before, right?
Yep.
Well, let's just plug it into the formula. That's going to give me the tangent of the first one, x, plus tangent of the second one, x, all over 1 minus tangent of the first one, x, times tangent of the second one, x. And then we simplify. Notice that in the numerator, we have a tangent x plus a tangent x. When you add them together, you get 2 tangents of x. All over in the denominator, you have 1 minus, but then you have tangent times tangent, and tangent times tangent is tangent squared when the arguments are the same. So it's going to be tangent squared of x. So the tangent of 2x is 2 tangent of x all over 1 minus tangent squared of x. Good deal. So far, we have now proven all of the double angle identities. If you may be thinking, well, what about cosecant, secant, and cotangent? Well, then you just use the reciprocal identities and then use the double angle identities for sine, cosine, and tangent. Good deal. So, number 2. Find the exact values of sine 120 degrees and tangent 120 degrees by using the double angle identities. And again, notice that it says double angle identities. If you don't use those, well, then it doesn't quite work out. So, let's look at the first one, the sine of 120 degrees. Now, the double angle identity says that then I want to find the sine of 2 times something to give me that 120 degrees. If you're having trouble with this, this isn't that hard, obviously. But really what you want to do is you want to say, when is 2x equal to 120? And what do? Divide by 2. So 120 divided by 2 is 60. Obviously, you could have done that in your head. But I'm doing that to help you in the future whenever it's much more difficult with angles, specifically the radians. Remember, dividing by 2 is the same thing as multiplying by 1/2. So there we go. We want to find sine of 2 times 60 degrees using the double angle identity. Now, sine's double angle identity is probably the most commonly used and the easily seen double angle identity. So let's come back up here. What was it again? It is 2 sine of x cosine of x. So I'm going to put this as 2 sine of the angle here, which is 60 degrees, times cosine of the angle here, which is 60 degrees. Just plugging that 60 degrees in for the x there. And then just simplify. So this will be 2 times, what is sine of 60 degrees?
One.
Yeah.
Square root.
The other one, yeah. Square root of 3 over 2. Times cosine of 60 degrees.
1/2.
1/2. Wonderful. Now, of course, notice the 2, then 1/2, they cancel. What am I left with? Square root of 3 over 2. Good. 2 times 1/2. What is it?
I don't know, but like, could you just determine what the answer would be just by?
Just by knowing it? Yeah, you should know this.
Yeah, I should just know 120 degrees, like sine of 120 degrees.
Yeah. Because the reference angle is 60 degrees. And it's in the second quadrant, so sine should be positive. But we didn't want to do it that way. We wanted to use the double angle identity. Yes. Again, if you didn't do it with the double angle identity, then it would be wrong. Good. Excellent. So let's do it now with tangent of 120 degrees. By the way, just out of curiosity, before we actually go through this, can you figure out what the answer is going to be here? What's the reference angle for 120 degrees? 60 degrees, right? What is tangent of 60 degrees? Square root of 3, good. So if it's square root of 3 and it's in the second quadrant, is tangent positive or negative? Negative. So in the second quadrant, all students take calculus. Only sine is positive in the second quadrant. So it's tangent, which means that it is negative. So it's negative square root of 3. That's going to be our answer here. That's the easy way. Now let's go about this the hard way. Okay, so tangent of 120 degrees is the same thing as asking what is the tangent of 2 times 60 degrees? Well, the double angle identity for tangent. Coming in up here, tangent of 2x, where x is in this case 60 degrees, is equal to 2 tangent of x all over 1 minus tangent squared of x. There we go. So we're gonna have 2 tangent of 60 degrees all over 1 minus tangent squared of 60 degrees. And just a reminder, please do not forget the degree symbol on these. Now, I've already asked you, what is the tangent of 60 degrees? Square root of 3. So it's going to be 2 square root of 3 all over 1 minus. Now, notice in the denominator, the tangent squared would be the square root of 3 squared. What is the square root of 3 squared? 3. So it's going to give us 2 square root of 3 all over 1 minus 3. And what is 1 minus 3? -2. So this is going to be 2 square root of 3 all over -2. And notice the 2's cancel and there's a negative there. That makes that means that this is going to be negative square root of 3. And there you go. So the tangent of 120 degrees is in fact negative square root of 3, either way you do it. Good deal. Any questions about this one? No, not too bad.
Not too bad, no.
Not yet, at least.
Not yet.
What page do you get back quickly?
Do number 3 then. Have fun. I dare you. Alrighty, so let's look at this. Sine of 60 degrees using a double angle identity. So if I want to find the sine of 60 degrees, that's the same thing as finding the sine of 2 times 30 degrees, right? Well, using the double angle identity for sine, that would be 2 sine of the 30 degrees cosine of the 30 degrees. Of course, 2 is just 2. Times sine of 30, sine of 30 degrees is 1/2, and the cosine of 30 degrees is square root of 3 over 2. 2 times 1/2 is 1, leaving us with the square root of 3 over 2. And there we go. Now, if you're wondering, did I get this right? Well, it's not a guarantee, but it's a decent check here. What is the sine of 60 degrees? Square root of 3 over 2. So, yeah, it's right, at least numerically. Good. Any questions about that? No, not yet. Number 4, prove that the following is an identity. Now we're going to look at the sine of 3x. We're going to show that sine of 3x is equal to the sine of x times 3 cosine squared of x minus sine squared of x. Now, notice that this is not 3 sine of x cosine of x or anything like that, or 3 sine squared. It just doesn't work out that way. So the sine of 2x being 2 sine of x cosine of x, it's just easy. It's nice. It's the only one that looks that nice, to be honest with you. Even the cosine of 2x is not that nice. So let's look at the sine of 3x here. I'm going to go ahead and actually begin with what you might consider to be the less difficult side. But it's actually the more difficult side, which is the sine of 3x here. Now, the reason I'm beginning there is because if I began over here, would you know where to begin there to make it look like the sine of 3x? No. So let's go ahead and begin with the sine of 3x. That's the side we don't really know. Now, the sine of 3x, I can think of this as one of 2 different ways. It really doesn't matter what way you think of it as. I can think of that as sine of 2x plus x, or the sine of x plus 2x. It really does not matter which one you choose, because again, addition has a commutative property, so it doesn't really matter which order you put it in. So I'm going to go ahead and use the sine of a sum formula. So now, can you think of what the sine of a sum formula is without looking at it? In other words, what is the sine of alpha plus beta?
Sine alpha cosine beta plus sine alpha, or yeah, sine beta and cosine alpha.
That will work. The way that I write it down is I do cosine alpha, sine beta, but the way that you wrote it down is perfect fine as well. Okay. Good. Now that we actually remember our sine of the sum formula, let's go ahead and plug in what we have here into that formula. Well, the sine of the first one will be sine of 2x. Cosine of the second one is just cosine of x. And then plus cosine of the first one, which is 2x, times sine of the second one, which is just x. All I've done there is I have used the sine of the sum formula. Notice, though, that now I have to use the double angle identity for sine, and I do know that. So what is the double angle identity for sine?
And then square root of root 2.
No, that's the sine of 60 degrees. I want the sine of 2x. What is that? There we go. 2 sine x cosine of x. That is the double angle identity for sine. So all of that has become 2 sine of x cosine of x. We still have this extra cosine of x there. So times cosine of x. And then plus, well, now notice that we have cosine of 2x. I need to use its double angle identity. Unfortunately, there are 3 of them. Cosine squared of x minus sine squared of x, 2 cosine squared of x minus 1, 1 minus 2 sine squared of x. And the question is which one should you choose? Well, you can choose any of them you want. Go away. You can choose any of them that you want, but there is one that will be better than the rest. So let's try and think about which one do we need. Let's look at this identity here, or this right side of the identity. Notice if I distribute the sine, that's going to give me 3 sine of x cosine squared of x, right? And then minus sine cubed of x. Well, here's the thing. If cosine of 2x is here, if I replace cosine of 2x with cosine squared minus sine squared, that will help me out more than the rest. So I'm going to put that in parentheses, cosine squared of x minus sine squared of x. But as I said, you could plug it in with any of those identities and you can still manipulate it to be what you wanted. And then times the sine of x here. Notice that I can combine the cosine times cosine as cosine squared there, and I can distribute the sine. When we do that, that's going to give me 2 sine of x cosine squared of x, plus when I distribute the sine, that gives me sine times cosine squared, so sine of x times cosine squared of x. And then minus, and over here, sine squared times sine is sine cubed of x. By the way, getting this sine cubed of x like that without a coefficient in front, that was the reason I wanted to use cosine squared minus sine squared. That was my impetus for using that one. Now, notice that 2 sine squared cosine squared plus sine, 2 sine cosine squared plus sine cosine squared. They're the same variables and functions, just with the different coefficients, right? Add them together, that gives us 3 sine of x cosine squared of x minus sine cubed of x. Good deal. Now, looking up here, have we finished? No. Because that is not that. Not yet. What can I do to get it there? No.
Factor out.
Factor out what?
Sine.
Sine. Factor out the sine, because that is a common factor there. And also, if you look up here, we need the sine out front, right? So let's factor out the sine. So this is going to give me sine of x times. Factor out a sine of x from both of those terms. What are you left with?
3 cosine squared x minus sine squared x.
There we go. Is that the right-hand side?
Yeah.
Yes, it is. So again, that's telling me sine of 3x here is sine of x times 3 cosine squared of x minus sine squared of x. QED. We're done. Good deal. Any questions about that? No? Not yet, at least. I think you know what's coming. Prove it. I dare you. Actually, no. I don't dare.
Put a double dog there.
No, that's for later. Okay, so notice that this one is tricky, right? It can be interesting. We're going to begin this one the same way we did the other one, with cosine of 3x. So this is going to be cosine of 2x plus x, or x plus 2x. It really doesn't matter which one you choose. So in this case, I'm going to replace the cosine of 2x plus x with the cosine of a sum formula, which would be the cosine of the first one, 2x, times cosine of the second one, x, and then minus the sine of the first one, 2x, times the sine of the second one, x. Cosine, you always use the opposite between them. And of course, you have to use the same functions for them to be even. Now, cosine of 2x. Well, we have 3 different possibilities. Cosine squared minus sine squared, 2 cosine squared minus 1, and 1 minus 2 sine squared. I mean, honestly, you're just going to have to start choosing and just see which one works. I'm going to go ahead and begin with the cosine squared minus sine squared, just because, for no other reason than I have no better idea. So cosine of 2x is cosine squared of x minus sine squared of x. But notice that I still have that cosine of x out front here, or out to the side here. And then minus the sine of 2x. There's only one identity for that one. And it would be 2 sine of x cosine of x. Times that sine of x at the end still. Good deal. Any questions about what I've done so far?
That's just the identity, right?
Yeah.
You wrote down?
Yeah, I'm just replacing those with their identities. Good. Outstanding. Now, be sure to distribute the cosine to both of those terms and make sure you multiply these signs together. So this is going to give me cosine cubed of x minus sine squared of x cosine of x, and then minus 2 sine squared of x cosine of x. And then notice that sine squared of x cosine of x, they're the same thing, right? So add them together, -2 plus -1 is -3, which gives me that this is cosine cubed of x minus 3 sine squared of x cosine of x. And if you wanted to, you could flip that around, making that cosine cubed of x minus 3 cosine of x sine squared of x. And that should be our identity. So there we go. This is the cosine of 3x. Good deal. Any questions about that?
So would that work with like any identity? Like if I were to pick any?
You might have to do a little more work, but you can get there. Would any be more difficult than the others? 1 minus 2 cosine, no, 1 minus 2 sine squared. Yeah, it would take a little bit more work, but you could get there. Good. Other questions? No? Number 6 says find the exact value of cosine of 75 degrees using the half angle identity. Well, because we're talking about half angle identities now, I feel the need to actually prove the half angle identities. So let's do that. I'm not going to need much room here, so I'm going to take the bottom, say, third of the page to prove this here. So let us begin with the following. What is the cosine of 2x? Well, actually, let me turn this around. Let me put the cosine of 2x on the right-hand side. The cosine of 2x. We've proven that it was actually 3 different identities, right?
Yep.
The first identity was that it was the cosine squared of x minus sine squared of x, right? That was one. Another one is that it was 2 cosine squared of x minus 1. And that would be the cosine of 2x there. And the third one was that it was 1 minus 2 sine squared of x. And that's going to still be cosine of 2x, right? All I've done here is I have just rewritten the 3 double angle identities for cosine. I just flipped them around from the normal order that you see them in. Now, I'm going to go ahead and take this middle one here. The 2 cosine squared of x minus 1 equals cosine of 2x. And what I'm going to do is I'm going to take this, I'm going to solve for the cosine of x, which is over here on the left-hand side. To do that, I first need to add 1 to both sides. So it's going to give me 2 cosine squared of x equals cosine of 2x plus 1 or 1 plus. It likes 1 plus. So we have 1 plus cosine of 2x here. Then, of course, divide everything by 2. So that means that cosine squared of x is equal to 1 plus the cosine of 2x all over 2. Now, if I'm trying to get the cosine by itself, it means I need to get rid of the square using the square root property, right? So it means that the cosine of x is equal to plus or minus the square root of 1 plus cosine of 2x all over 2. Notice that that 2 is underneath the radical as well. So you're taking the square root of that entire fraction. Here's the thing though. I don't like having a 2x here and an x here. So if I let u be 2x, then u over 2 is x. In other words, this is telling you that the cosine of u is equal to plus or minus the square root of 1 plus the cosine of u all over 2. Sorry, that's u over 2. My apologies here. That's u over 2. There we go.
Oh, okay. I was like,
Yeah.
like which
My apologies. And look, that is the half angle identity for cosine up here. The half angle identity was plus or minus the square root, sorry, cosine of x over 2 is equal to plus or minus the square root of 1 plus the cosine of x all over 2. But notice that's x over 2 and x. It doesn't really matter what the variable is. Variables are just dummy variables. They can be whatever they want. So there you go. That is the half angle identity for cosine. Now, we did that using the double angle identity for cosine, right? And you would think that to find the half angle identity for sine, we would probably use the double angle identity for sine as well, right? But that's not true. We're actually going to use the cosine, the double angle identity for cosine as well, but not that one. We're going to use a different one. We're going to use this one down here. Because notice we can get the sine by itself. So we're going to do this all again with 1 minus 2 sine squared of x equals cosine of 2x. That is another double angle identity for cosine here, right? Now, I'm going to cut to the chase. We subtract 1, divide by -2. So that means that the sine of x, or sine squared of x, I'll go ahead and say, is equal to 1 minus the cosine of 2x all over 2. They've changed signs because I divided by -2. I just distributed the negative there. Sine squared of x, my apologies. And of course, that means that sine of x would then be the plus or minus the square root of 1 minus cosine of 2x all over 2. And by the same reasoning, that tells me that the sine of u over 2, the half angle identity for sine, is equal to plus or minus the square root of 1 minus cosine of u all over 2. But you can, of course, replace the u with an x instead if you want. Good deal. So we've just proven the half angle identity for sine. Is everyone okay with that so far? Yeah. No, not okay. What's wrong?
That's hard.
I'm not asking is it hard, I'm asking are you following? What are you not following?
I explain.
You're killing me, Smalls.
Wait, how does the 2 like how does it go from out of the square root to the like this to the other side of the equal sign? Does that make sense?
No.
Like
What part?
Like the 2x right there?
Right here?
No, but like almost, yeah, right there.
How does it go from here to over here? It
Yeah.
doesn't.
No, it doesn't?
No. So what's happening here is I'm introducing a change variable. Let u equal 2x.
Oh, okay.
Okay, if u is 2x, then that means that u over 2 is equal to x. So I'm replacing this x with u over 2. And I'll replace this 2x with u.
Oh, okay.
Yeah, that's all that's happening there. It's just a change of variable.
Oh. Got it.
Okay, so that's the half angle identity for sine. But notice we have one more function we need a half angle identity for, and that is tangent. So here's the thing. The tangent, I'm gonna use x over 2 is equal to, but notice the tangent is just sine over cosine, isn't it? So that's sine of x over 2 divided by the cosine of x over 2. But what did we determine sine of x over 2 was? Well, we just figured out it was plus or minus the square root of 1 minus cosine of x all over 2. And then all over plus or minus the square root of cosine of x over 2 was 1 plus cosine of x all over 2. Notice the only difference between sine and cosine there is that it's a minus instead of a plus for sine. Now, here's one of the cool things. First of all, we just put one big plus or minus out front and then combine this into a single radical as 1 minus cosine of x over 2 all over 1 plus cosine of x over 2. But notice that the 2's are on the same side on each side of those, so they're in the denominators of both numerator and denominator, so they will cancel each other. And what am I left with?
Minus cosine x over, over 1 plus cosine x.
Yep. So that's telling me that the tangent of x over 2 is equal to plus or minus the square root of 1 minus cosine of x all over 1 plus cosine of x. And there we go. That is the half angle identity for tangent, or at least one of them. Any questions so far about this one? I'm gonna go ahead and put a star next to it here. Now, I'm gonna keep going with this. So I'm gonna say that the tangent of x over 2 is equal to plus or minus. Now we still have that square root here, make it a very long square root. And then it was 1 minus the cosine of x divided by 1 plus the cosine of x. To get the other half angle identities for tangent, we need to go ahead and get rid of that square root somehow. Now, to do that, I'm going to go ahead and multiply by 1 plus cosine of x on both top and bottom. Now, you could do it as 1 minus cosine of x as well. I'm just doing that just because I want to. Now, how does this simplify? Well, it becomes plus or minus the square root of, notice that in the numerator, we have 1 minus cosine times 1 plus cosine, and that's a product of conjugates, which when you multiply together will give you a difference of squares. So square the 1, what's 1 squared? 1 minus square the cosine, what's cosine squared?
Cosine 2x.
So cosine squared, yeah. And then all over 1 plus cosine times 1 plus cosine, I'm gonna go ahead and write it down as simply 1 plus cosine of x squared. Now, why has that helped me? Well, look at the numerator there. In that numerator, it's 1 minus cosine squared. What is 1 minus cosine squared?
Oh, it's
1 minus cosine.
sine
It's sine squared. 1 minus cosine squared is sine squared, right? So we have plus or minus here, and we have that big square root of sine squared of x all over parentheses 1 plus cosine of x all squared. Good deal. Now, looking at that expression here, we're gonna have the plus or minus out here, and then the numerator is the square root of the sine squared of x all over. In the denominator, it's the square root of parentheses 1 plus cosine of x all squared. Now, these are different things here, and they're different things for a reason. I'm going to put a plus or minus here. The square root of sine squared. What is the square root of sine squared?
Line X, orange sign. No, I don't know.
It's technically the absolute value of sine.
Hmm.
Do you remember back in 1414 when we talked about the square root of x squared is just the absolute value of x? You probably don't. We don't emphasize that very much. In other words, the reason for that is because what if x was -2? -2 squared is 4. Square root of 4 is 2, right? Not -2. So if you're taking the square root of something squared like that, that will give you the absolute value of x. Now, if it was the other way around, the square root of x being squared, that does give you x. But it does matter where the squared goes here. So over here, when you have the square root of sine squared of x, that's just going to give you the absolute value of sine of x. And then all over in the denominator, the square root of 1 plus cosine of x all squared. You might think it's the absolute value of 1 plus cosine of x. And you're correct, it is. But here's the thing, cosine's range is between -1 to +1. The smallest it can ever be is -1, right? What's 1 minus negative, what's 1 plus -1? What's 1 minus 1? 0, thank you, yes. You're welcome. I asked you, what is 1 minus 1 in your college trigonometry class, and you hesitated. That's how crazy your brain is right now. So 1 minus 1 is 0, right? That's the smallest it can ever be. What about the largest? The largest cosine it can ever be is +1, right? So 1 plus 1 is 2. So that denominator, the lowest it can ever be is 0. The highest it can ever be is 2. From 0 to 2 in that denominator there, right? Is that ever negative? Then why do we need the absolute value around it? We don't. So that denominator is simply 1 plus cosine of x. That's why we don't put that absolute value around it. Now,
Would be wrong.
one more thing here. Do what?
Would be wrong if we put that.
No, but it makes it more difficult right now. One more thing here. The left-hand side is tangent of x over 2. You can go and prove on your own time that the plus or minus the absolute value of sine of x, or sorry, not the plus minus, the absolute value of sine of x, sorry, not that, sine of x will always have the same value as tangent of x over 2 in sine, as a plus or minus. So when sine is positive, tangent of x over 2 is positive. When sine of x is negative, tangent of x over 2 will be negative. And that has to do with the periods and frequencies of these. Because sine and tangent both are 0 at 0. And the fact that we have an over 2 over there, the period for tangent, instead of pi over, it's pi over 1/2, which gives us 2 pi. So as a result, sine of x and tangent of x over 2 have the same period. And so they'll have the same sign at the same places. So therefore, this is simply the sine of x over 1 plus cosine of x. That's the tangent of x over 2 equals sine of x over 1 plus cosine of x. Apparently, I didn't have enough room. I have one more I need to prove here.
Double back, please.
Just add a page there. Okay, so we're going to go ahead and begin where we just ended. We just ended at the tangent of x over 2 is equal to the sine of x divided by 1 plus cosine of x. Now, to get to the other one, it's actually pretty easy this time. I'm going to multiply the numerator and denominator by the conjugate of the denominator this time, which is 1 minus cosine of x. Now in the numerator, don't multiply those together. That's going to give you sine of x times 1 minus cosine of x. All over in the denominator, 1 plus cosine of x times 1 minus cosine of x. What was that? Or what is that?
What was it again?
What is 1 plus cosine of x times 1 minus cosine of x? Good, 1 minus cosine squared of x. Wonderful. But here's a question for you. What is 1 minus cosine squared of x? Sine squared of x. Good. So the numerator just it's still sine of x times 1 minus cosine of x, right? Oh, look, there's a common factor of sine of x. So if I cancel stuff, the numerator is just going to be 1 minus cosine of x, and the denominator will be sine of x. And therefore, that is the tangent of x over 2. That is your third identity. There we go. So we have several different identities here. The first one was the cosine of u is what we used, but it didn't matter really. So cosine of x over 2 is equal to the plus or minus square root of 1 plus cosine of u all over 2. And over here, sine of u over 2 is plus or minus the square root of 1 minus cosine of u all over 2. Then over here, we have the tangent of x over 2 is equal to plus or minus square root of 1 minus cosine of x all over 1 plus cosine of x. The tangent of x over 2 is also equal to the sine of x all over 1 plus cosine of x. And then, of course, we have this last one of tangent of x over 2 is 1 minus cosine of x all over sine of x. Wonderful. So we just proved all of the half angle identities. Yay! Everyone's so happy and excited. I'm so excited. Let's look at number 6. Find the exact value of sine of 75 degrees using a half angle identity. So, cosine of 75 degrees. Well, cosine of 75 degrees is equal to the cosine of something over 2. What should that something be? If 75 degrees is the angle we want, but we want to have it something over 2, what should that numerator be? 150. Why? Because you need to double the 75, right? So it'll be 150 degrees as a result. Now, in your head, here's what you should be doing. X over 2 is equal to 75. Multiply by 2 on both sides, so x is equal to 150, right? So there we go. We're going to use the half angle identity for cosine when we're looking at cosine of 150 degrees over 2. Now, in this case, the u slash x, or however you want to memorize it, if we come up here, cosine of x over 2 is plus or minus the square root of 1 plus cosine of x all over 2, right? So coming down here, this is equal to plus or minus the square root of 1 plus cosine of the x value, which is the numerator, and the numerator here is 150 degrees, all over 2. And fantastic. Now we just need to simplify this. It's going to be plus or minus the square root of 1 plus. What is the cosine of 150 degrees? How about this? What's the reference angle for 150 degrees?
Square is 2.
What is the reference angle for 150 degrees?
30.
It's 30 degrees, right? What is the cosine of 30 degrees? Square root of 3 over 2. Good. And cosine is in the second quadrant here. Is it positive or negative?
It'd be negative.
So it's negative square root of 3 over 2. That's what the cosine of 150 degrees is. So it's going to be 1 plus a negative square root of 3 over 2 all over 2. Good deal. Notice that this then is going to become the following. We have plus or minus. We have the square root of 1 minus square root of 3 over 2 all over 2. Here's the thing though, I don't like seeing a complex fraction, right? So I'm going to go ahead and multiply both numerator and denominator by the LCD of all denominators there, which in this case just happens to be a 2. Notice that I can then distribute the 2. And what does that give me? Well, it gives me plus or minus the square root of 2 minus the square root of 3 all over 4. Now, cosine in the second quadrant is negative, so I'm just going to use a negative instead of the plus or minus because that's what we need here. I'm going to take the square root of both the numerator and denominator separately. So we're going to have the square root of 2 minus the square root of 3 in the numerator. And then all over in the denominator, what's the square root of 4? 2. There we go. So that's telling me that the cosine of 75 degrees is, we're in the first quadrant. Y'all should have yelled at me. That's a positive there, not a negative. Right, 75 degrees is first quadrant. Yeah, not second.
Where did you get second quadrant?
That was the 150 degrees.
Oh, yeah.
Yeah. So cosine of 75 degrees is equal to the positive square root of 2 minus the square root of 3 all over 2. Now notice that here, the way that I've written this radical is that it is clearly only the numerator. And you have this divide go across that entire thing. Be very careful about that, because you only want the radical in the numerator. Good. Go back to what we've already done in the past, though. We've already figured out the cosine of 75 degrees in the past, haven't we? What was it? Well, in the past, wasn't it the square root of 6 minus the square root of 2 all over 4? Are you just saying that, or
No, I remember that. I actually.
or do you actually know for absolute certain that that's exactly what it was?
Well, I know there's another one, but
Yeah, there were a lot of them, so I want you to go back and look.
all right.
Was it that?
With 75 degrees?
Uh-huh.
With
For cosine, yeah.
Uh,
Cosine of 75 degrees.
oh, I don't see it.
Yeah, no.
It's fine.
I see a sine of 75 degrees. Do we have a cosine of 75 degrees somewhere here? Did we? Second page. Ah, there it goes. Yeah, square root of 6 minus square root of 2 all over 4. Awesome, thank you.
Was it 3.3?
Yeah, 3.3 second page. So notice the cosine of 75 degrees is square root of 2 minus square root of 3 all over 2. And so as a result, this is true. That is an exact value. That is what cosine of 75 degrees is. But cosine of 75 degrees is also this. It's just a different way of writing down the same number. That's all it is. Any questions about any of that?
So like if we already know what it is.
No.
And you already know. You know.
You have to do exactly what it says. The question specifically says using the half angle line derivative, which means your answer needs to be in the form of what the half angle line derivative would do.
Okay.
Yeah. I mean, you can use it to check it.
Yeah.
Yeah, you can do square root of 2 minus square root of 3 all over 2, enter, and then go top end square root of 6 minus square root of 2 all over 4, enter. See that the left hand side, the first one equals the second.
Okay.
Other than that, though, no, you can't.
No, sorry.
Good try though. I thought that whenever I took trig too. By that I mean whenever I taught trig, and because I never actually took it.
Oh, you know, it's okay.
No. Good deal. Any questions? By the way, me not taking trig was actually a bad thing.
Lucked out.
Do what?
You said you lucked out.
No.
No,
Lucked out means it was a good thing.
it's hard.
I know. But calculus was more difficult as a result. Hey, guess what? You have another one to do. This one, the sine of 75 degrees. Have fun with it. You're like, I knew it. Yeah, you did. Okay, so let's go ahead and look at this. We are looking at the sine of 75 degrees. Now the sine of 75 degrees, if we're using the half angle identity, that'd be the sine of something over 2. Now the question is what is that something? Well, if you want to know x over 2 equals 75, how do you solve for x? Multiply by 2, so that means that x is equal to 150. So that's why the numerator here is 150 degrees. So it's going to be, now, I could use plus minus this entire way, but in order to keep from making the same mistake I did last time, 75 degrees is in what quadrant? The first quadrant, and sine is what in the first quadrant? Positive. So I'm just going to use the square root instead of plus minus. There we go. And then 1, but instead of minus, at this time it was plus the cosine of the 150 degrees. Wait, no, it's minus. My apologies. Wait, something's wrong here. And then all over 2. Fantastic. Now we've already discussed 150 cosine of 150 degrees would be negative square root of 3 over 2, right? So this would be the square root of 1 minus a negative square root of 3 over 2, all over 2. Minus the negative, of course, is a plus, which means that this is the square root of 1 plus the square root of 3 over 2, all over 2. And of course, I can multiply both the numerator and denominator by 2 to get rid of that denominator. It's going to give me the square root of 2 plus the square root of 3 all over 4. And when you take the square root of the numerator and denominator separately, that's the square root of 2 plus the square root of 3 all over 2. And there you go. This is the sine of 75 degrees. Any questions about that? Here's a question for you. What's the tangent of 75 degrees? Well, here's the thing. You have actually 3 different formulas you could use, but this would be the tangent of, again, 150 degrees over 2, right?
Yeah.
I can use any of those, but if you look at them, you won't really only ever want to use 2 of them. Either the sine over 1 plus cosine or 1 minus cosine over sine. Either one of those is fine. I'm going to use the first one, sine over 1 plus cosine. So this would be the sine of 150 degrees all over 1 plus cosine of 150 degrees. Now, sine of 150 degrees is the same thing as sine of 30 degrees, which is what? Good, 1/2. All over 1 plus cosine of 150 degrees we already determined was negative square root of 3 over 2. So notice that if I multiply both the numerator and denominator by 2 here, that's going to go ahead and give me 1 over 2 minus the square root of 3. But we generally don't like having a radical in the denominator, which is the reason why we're going to need to multiply both the numerator and denominator by the conjugate of the denominator, which would be 2 plus the square root of 3. So distribute the 2 plus square root of 3. That gives me 2 plus square root of 3 in the numerator. In the denominator, that's a product of conjugates, which means it'll give us the difference of squares. Square the 2, that gives us 4, minus the square of the square root gives us the 3. And of course, 4 minus 3 is just 1, leaving us with 2 square root of 3. Sorry, 2 plus square root of 3. And that is the tangent of 75 degrees. And if you go back and look, that's exactly what we got before. No big deal. Any questions about that? No? No questions? You're all thoughtless people? Awesome. All righty. That's it for today.